In this video, we're going to talk about some of the tools that we've learned this week in our videos and how to use them to estimate sample sizes. If we know the margin of error that we want to use to construct our confidence interval, we can figure out about what sample size we should use for our study. So if I know ahead of time how wide I want my interval to be, or how much lax I have in my calculations, I can use that to figure out what an appropriate sample size would look like for my study. The formula for sample size is going to vary depending on the parameter we're estimating, because we're picking off the margin of error from our confidence interval formula, and we saw that changed depending on what we were estimating. Remember that your margin of error is the thing that comes after the plus or minus in the confidence interval formula. So for a mean, when we know the population standard deviation, we know that our margin of error is equal to our critical z-value times the standard error, which is sigma over the square root of n. I would substitute in all of the values I have, margin of error, critical value, standard deviation, and I would solve for n. We know when we're estimating means and I don't know the population standard deviation, that formula is almost identical, except that now it's the student t distribution for a critical value, and we're estimating sigma with s, our sample standard deviation. When we're estimating proportions, we know that we go back to the z distribution, assuming we've met that condition for normality, and that the standard error for proportions is p prime times q prime over sample size. For proportions, because we know that we calculate proportions as number of successes over a sample size, if we're trying to estimate a sample size before we've done the study, we often won't know p prime and q prime. In that case, if you don't know p prime and q prime, you're going to assume that they are 50-50, 0.5 and 0.5. Once we've set that formula up, it's just a little bit of algebra to isolate n in the equation. We're going to go ahead and do two examples so you can see what it looks like for different kinds of confidence intervals. So our first example says a sociologist wishes to estimate the average number of car thefts in San Francisco within 2 cars. She wishes to be 95% confident, and from a previous study, the standard deviation was found to be 4.2 cars per day. How many days should she select to survey? So the first thing is I know that I'm being asked for a sample size because it didn't say estimate a mean, estimate a proportion. It asks how many days should I survey? That's a sample size. That's the same as asking how many people should I survey. So this is what's telling me that I'm looking for sample size. And then I'm going to pick through and look at what I'm given. I'm asked about estimating an average, so I know I'm in one of the 2 boxes for mean. I know that I want to estimate my average within 2 cars. And when they use that phrase within, that's usually the margin of error. It means I want my margin of error to be plus or minus 2. We're also told we want to be 95% confident. We know that's our confidence level. And we're told that from a previous study, the standard deviation was found to be 4.2 cars per day. And the assumption is that is a population standard deviation. So let's go ahead and list what we're given. So we know our margin of error is 2. Our confidence level is 95%. Our standard deviation is 4.2. And I'm asked for sample size. So looking at what I have and what I want, I know I'm in this box up here. So I'm going to grab for that formula. Margin of error equals critical value times sigma over square root of n. So I need the critical value for a confidence level of 95. So off to the side, I'm going to build a little confidence interval here with my normal curve that is horribly drawn, and I am sorry, it's been a long day. I know that 95% goes in the middle. I want to know where those boundary values are, and I know I do that with inverse norm. Inverse norm asks for area, it asks for mean, it asks for standard deviation, it asks for tail. And writing on the edge of my iPad is hard. That's supposed to say center. And we've done this calculation at several points today. I happen to know that that's going to be 1.96, but you should check on my calculator if you don't believe me, or check on your calculator. Now that I have my CV, I'm going to plug in what I have and solve for n. So my margin of error is 2. My critical value is 1.96. My standard deviation is 4.2. And square root of n. So first thing I'm going to do is I'm going to divide both sides by 1.96. And that's going to cancel that guy. And I'm not going to simplify, I'm going to leave that as it is. So 2 over 1.96 equals 4.2 over the square root of n. And the reason that I left it that way is the variable that I'm solving for is in the bottom of a fraction. And as a mathematician, that makes me unhappy. When I have an equation like this, where I have a fraction equal to another fraction, we call those proportions. Different kind of proportion than in statistics. I know I have two ways to solve that. One, I can use the butterfly method, multiply, multiply. Or, for the truly lazy like myself, I know I'm allowed to do whatever I want to the left side of the equation, as long as I do the same thing to the right side. I'm going to flip both of those fractions. I'm going to find their reciprocals. So the left side's going to become 1.96 over 2. The right side's going to become square root of n over 4.2. And that becomes less scary to me as a mathematician. I know how to undo division. Fraction bar is a division symbol. I just multiply by the denominator. So both sides by 4.2. And that's going to give me 4.2 times 1.96 all over 2 is equal to the square root of n. And I know to undo square roots, I square. So I'm going to square both sides. So on my calculator, I should have 4.2 times 1.96 divided by 2 squared. And we get 19.9, or not 19.9, sorry, 16.9. And I can't have 16.9 of a person or 16.9 of a day, so we round this up to 17 days. in order to ensure that she's getting her estimate for the average number of car thefts within 2 cars, plus or minus 2 cars, she needs to survey at least 17 days. All right, let's try another one. Second example says obesity is defined as a body mass index of 30 kilograms per meter squared or more. A 95% confidence interval for the percentage of U.S. adults aged 20 years and over who were obese was found to be 22.4 to 23.5. What was the sample size? So first, they were nice and explicit. What was the sample size? So I know I'm looking for sample size. And they give me slightly different information here. First, they give me the definition of obesity, which is not helpful. That first sentence gives context to the problem. It doesn't give me a number that I need to use in my calculations. What they do give me is that I want to be 95% confident and that my confidence interval was between these two values. So I know that the confidence interval for this proportion was from 22.4% to 23.5%. I know when I build my confidence interval that the sample proportion should be in the middle, and then I subtract the margin of error that way and add the margin of error that way. Meaning the margin of error should be half the width of this interval from end to end. So I'm going to subtract those values to figure out how wide the interval is, and then I'm going to divide it in half to get my margin of error. So on a calculator, I want to do, and I'm going to convert these into decimals because when I do math with percentages, I always do them in decimal form. 0.235 minus 0.224, and then divided by 2. So we get a margin of error, which is this difference divided by 2, of 0.0055. So p prime plus or minus 0.0055. I know that I've got a 95% confidence level, and since this is a percentage or a proportion, I know that means my confidence, or rather critical value, is a z-score, and we know from previous problems it's going to be 1.96. I also notice, if I go back up here, I'm estimating proportions, I'm in this realm, and I don't have a p prime or a q prime. I have a z, I have an me, I don't have p prime, q prime. So we're going to go with the assumption of 0.5 and 0.5. If we're not given those sample proportions, and we probably wouldn't because we haven't done our sampling yet, assume these are equal. That'll give us the biggest estimate for a sample we could have. So let's go ahead and jump to our equation. We know the margin of error is equal to our critical value times our standard error. 0.5 times 0.5 over square root of n. I'm going to start the same way. I'm going to work from my outside in. Start by undoing that multiplication with some division. The next thing I'm going to do is I need to undo that square root because the sample size is underneath it. And I know I undo square roots with squares, so I'm going to square that whole thing and square this whole thing. I'm also going to do the 0.5 times 0.5 because I'm tired of carrying that around, so 0.25. So this is 0.25. And then I'm going to use the trick from last time. I know I can flip these upside down. I find the reciprocals of both sides. So 0.0, whoops, flip them upside down. 1.96 over 0.0055 squared equals n over 0.25. And I know my last step to undo that division by 0.25, I'm going to multiply both sides by it. 0.025. And whatever that comes out as on my calculator, that should be my sample size. So 0.25 times, and then 1.96 divided by 0.0055 squared. And we get a much bigger number. 31748.8, which would round up to 31,749. So if I want my margin of error to be this tiny, and notice that's less than 1%, because 1% would be 0.01. That's a tiny, tiny margin of error. If I want to be that certain in my answer, I need a very large sample. All right, if you have any questions on what you've seen, feel free to send me an email or drop by office hours. Otherwise, I'll see you in our next video.